Now the idea behind the review 2 is that you'll have a circuit level LNA that is optimized to meet the specifications. Now the LNA, most of you guys have selected the lab 2 circuit that I've given you and modified it. Now it looks somewhat like in this format. So you had an input match, you had a circuit transistor, then you have a intermediate match, then a transistor and output match. Now you are free to select the transistors, so you will see that when you play around with them you'll get different gains, different matching performance. So the idea behind the exercise is for you to select the right transistors. Now I'll probably want to talk a little bit more about input match because there was a lot of questions before the break about input match. Now my suggestion was like to keep it simple. The best thing would be to use the input match circuits that I've given in the lab 2, but you can also use other circuits. But I thought, since I've seen most of the people have used the standard lab 2 input match, I thought I'll explain a bit more about it. Now we've done in the class, let me just open it up. So we did input match circuits in the class. So we had the source, then we have an element, then we had another element, then we had the load connected to the ground. That's ground. Now we notice that we can either have a C-L pair or L-C pair like that. So that's the most basic matching circuit, and this is connected to the ground. Now in order to match for this particular circuit, we've already used very similar matching structure. So if I redraw this again, so what we've used is we had a capacitor, and then we had an inductor, and then a ground. Then we had the transistor, and then source connected to the ground, and then we had the drain, another circuit. So the drain also had a inductor and a capacitor, and then another inductor to the second stage. Now you are free to select. So these were grounded. So this is pretty much, and then we had the inductor and a capacitor. So that's the output. So this is pretty much the circuit that we had in the lab 2. You would notice there's a lot more components than the capacitor and the inductor in this circuit. So if I go back to, so this is my input match. I go into this circuit, so that's the capacitor. I had a M-lin elements on the left and right hand side. Then I had a T-junction and another M-lin. So this is pretty much just a capacitor, and that's the inductor. So that if I go back to this, so capacitor and the inductor. So inductor was like that in this circuit. So this inductor was on the other. So this is the same inductor. Then we had another capacitor that is not normal in the way normal. Yeah, when I did the teaching on the lecture, I didn't specify anything on the capacitor, but there's a reason why the capacitor is there. So if okay, so let me draw this back again. So we had the inductor, and there's a capacitor that's connected to the ground. The reason this capacitor is there is to actually isolate the RF coming from here and the DC that's used for biasing. So we need to isolate RF and DC. We don't want RF to go this way. We don't want it, so that's not what we want. We want the RF to go that way, right? So that's why we have a capacitor. What happens with the capacitor is this capacitor looks like a short circuit for RF. So this is a virtual ground for RF. So it doesn't see the circuitry behind that, which is probably a resistor and like a transmission lines and a power supply. I think we use 0.5 volt or something. So this circuit below this point is pretty much invisible for the RF, so it doesn't see that because of the short circuit capacitor. So that's why we had to use the capacitor. So you'll notice this same configuration is used throughout the circuit. So that's the most basic matching circuit you can have, and the more simpler it is, the better it is in terms of noise figure, in terms of matching, much easier to handle. So I wouldn't mind if you have a matching circuit like that. So that's why we did that in the class. So you can theoretically calculate the C and the L from the equations that we've discussed before for 14 gigahertz. Now to do that, you need the impedance at this point, right? So you can look at that impedance on a Smith chart for the transistor if you want. I'll talk about that probably in the class, but you don't really, or maybe I'll just show it to you guys now quickly. So if I want to look at the transistor, so which is the transistor here, I can plot this on a S parameter I can plot this on a Smith chart. Maybe I'll refrain from talking about it now just to keep everyone on the same track, because the idea here is to talk to you about input match. And maybe in the first lecture that we have, which is after the break, I will talk about this Smith charts and all that. Or I'll do a separate video anyway. Now let's going back to input match. So it's pretty much a matter of tuning this inductor and a capacitor and this capacitor here to get the input match. Now I did play around with this for a while, say probably half a day or something. I managed to get a decent matching. So if you look at these optimized levels, this is -8 dB. So you can go to your optimizer goals and then add optimizer goal and then add this value. So I already had that measurement. So in this optimizer goal S11, I've selected the LNA S11. Measurement has to be less than the goal, and between this band and the goal is -8. Don't worry about the weight at the moment because you're not optimizing, you're just manually tuning it. That will set out these values because your frequency range is 12 to 16. So that's the first parameter that you had in the assessment. Then you need to have 25 dB, greater than 25 dB gain, a flatness about 1 dB, return loss, which is S11 less than -8 dB. Noise figure 2 dB. PSAT, okay, I'll talk about this now in like 5 minutes after this discussion. And then your VDD is 3 volt. Okay, ID maximum has to be 15 to 25 milliamps, 2 by 2 millimeter. Okay, QFN, that comes out later in the layout stage. Now I got the S11 return loss set, S21 the gain 25 dB mark, so I'm barely there. I'm slightly lower, so you probably can do fine tuning. It's pretty much your task to fine tune, but this circuit is tunable. Now you notice this green curve, the K factor, is the stability factor, is not really good because it has to be above 1. So it's not very stable in here, but maybe there are things that you guys can do to get the K factor up above 1. Now the noise figure has to be less than 2, so that's it corresponds to the right hand axis. So noise figure is this blue curve, it's less than 2, so you should be able to decently tune the circuit to meet almost all the specifications. Now if it's a 0.1 dB, 0.2 dB lower, I think it's because don't worry about it too much. As long as it is above that, like just try to make it meet the spec, not like I did. and then because when you do the later stages you're going to lose this gain, so it can be done if you put more time to it. Now this is, let's say this is sort of the final circuit simulations. Now the problem is you have this, let's say we're satisfied with this circuit simulation. If I go back to my input match, I have capacitors and inductors, ideal ones. Now how do I make them on a circuit, like, because I'm not going to round a coil to make a 0.33 nanohenry. So on a layout you can't have a coil, you have to have it in a microstrip line. Now so specifically targeting review 2, you don't want to have these ones as your final. You will need to have them in a microstrip like the Emlyn version at least. Now to do that, I can get an Emlyn block like this. I copy and paste it. And then I can, so what I'm trying to do is a longer, so let's make it with 5. A longer transmission line looks like an inductor, but length of 10 micrometer is not going to look like an inductor. So what I can do, I'll first go, I'll just toggle it, re-simulate this. So when you tune, you basically have to get your tuner and then say select the input match, say tune this. So you'll notice that it just tunes around, right? So that's what you need. So gain didn't change much with the input match. It's mainly the return loss and the noise figure. So I did a bit of tuning, because if I do a video on tuning, then it will be a long video because it's just a trial and error. But this is the fastest way to do the tuning. If you calculate the ways, using the ways that we taught you in the lecture, it's going to take you a long time because you're only calculating it for a particular frequency, and that might not work exactly because you have other circuitry around it, right? So it will take you a long time because you will only have L and the C and L values. When you add the other stuff, they will have some inductors, you have capacitors, resistors, all these, it will change your value. So it's best to tune and get a feeling for it, and this is what's followed in the when you do tuning like in practically. You know, I come back to here, I say I'm satisfied with this, I'll control F this, so that's freezed, the trace is freeze, because I'm going to change the components now. I'll get a microstrip line, just copy paste it. So maybe let's say it's 100 micrometers long, and I'll replace this, and then so instead of the inductor, I'm replacing that with a microstrip line. So let's see what my so that my gain dropped, but things bad. So how do I know what would be the right length? So the best thing probably to do is I'll make this tunable. So I will make this tunable. I can go back to my tuner. So that's this 100. Now I can look at my graph and tune this. Okay, so it's getting there. Okay, so let's say this is let's say it won't be exactly the same, but it'll be close enough. So okay, 370 might, I'm happy with this. So let's say that's good enough for me. So that'll be my 370. So what happens is this line has to be 370 micrometers long. Now practically this line, if it's 370 micrometers long, you can look at the layout. So if you press this button on the view layout button, and let's click this, select this, then press the view layout button, you'll notice there's a long line highlighted. So that long line is your inductor. And you don't want to have a long line because it will take up your space. You don't have much space to spare. So what we can do is we can wind this so it looks like an inductor. Now luckily the Win library has some of the spiraled inductors in it. We just have to tune it. So if you go to libraries, WinPE 1500, and then you go to passives and spiral. So you have round or square. So if I just take one of the square ones, I've dealt with only square ones, so but you're free to use round ones if you want. I think it will probably take a bit more time for EM simulations. Maybe I could be wrong, but so this is a spiral. So if you look at the layout of this, it looks like this, and so this long line that you had, you could wind it so it takes up less space. Now this particular spiral that we picked this one, it has about 571.7 picohenry. Now we don't know what's the amount of inductance in this line, because we can probably calculate using traditional formulas, but is it worth it, or we could mesh that with the spiral length? So what the library provides you is a variable scalable square inductor. So you could technically take this and then replace it. So the idea is now this spiral inductor is going to replace this microstrip line. Now given this is 370, so if I had number of turns, so you can look at the parameters here. It tells you all the what each variable stands for. N stands for the number of turns. So if I make it, so let's go to this. At the moment it has 13 turns, so which means it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 turns. So I think it's obviously comparing this and that, this is much shorter, so we want lesser turns. Now if I want lesser terms, I'll have to make this 5, say. So when I do that 5, I will not, you can notice in the layout it has got smaller. So 1, 2, 3, 4, 5. So 5 turns. I don't know whether we can do 4 turns. We can try the 4 turns. It doesn't let you do 4 turns. I think it's probably, yeah, it doesn't let you do 4 turns because it's 1, 2, 3, 4. It doesn't, the particular way it was built, it's called parametric cells. They don't let you do that. Well, we can deal with 5 turns, I think, because we can make this shorter so it matches this length. Now if it is about 370 and the width of that line is 11, this width is 5, so let's check if we can make this 5. It just lets you do 7. It doesn't let you do less than, so it's okay. We can maybe make this 100, 100, 100. How does it look like now? Okay, maybe we can try this. So we will connect these 2 points. So I can toggle enable this because you don't want to have 2 inductors in parallel. Then simulate it. We just got lucky because we are close enough. Now if you want to tune it a bit more, what you can do is you can put a variable here. So I can get a variable. Oh yeah, let's do it this way. So we'll get a variable length 1. So let's say this is close to 100, 100, and I'll make this length 1, and then I'll make this one plus 10 minus 20. Just randomly I'm putting numbers. Okay, so we'll make this a variable. Then I can go back, and so this lane 1 became a variable. I can go here. Okay, let's simulate this. And then tune it so that I can pretty much match the previous one. So that's what you need to do. So when you do that, you'll no longer have an inductor, you'll no longer have a straight line, you'll have a wind inductor. And if you look at the layout, you'll have an inductor like this, which is small compared to a longer line as before. Okay, now we will also need to check, so that will replace your inductors. So the capacitors, if you look at that, this doesn't have a layout associated with it. So we want a layout if you want to make like a circuit out of this. So we will have to go back to here, and then from the Win library we'll have to get a capacitor. So if you go to the capacitors, there's a mean capacitors. Now capacitor, it's much easier because it says 6618 picofarad. So you just have to make the width and length of this capacitor to go close to 6618, and it is quite close enough. So if I replace this cap with this cap, I should see minimum change, I think. Yeah, so it's very minimum change. So now if you look at the layout for this capacitor, there's a, see this one, that's the capacitor. So if you look at the 3D layout of this, the top plate, lower plate, it will give you the capacitors. Okay, now coming back to this, so we are pretty much trying to arrange our circuit, right? So the whole idea is you need to replace all your capacitors and inductors with the Win P1500 capacitors and inductor model. So you will have microstrip lines, capacitor, proper drawings when you come to the later stages. So at the review 2, I expect you to have these capacitors, inductors, proper capacitors, inductors with the tuned values. You can do the same with the resistors. You can get the resistors, get the TFR and put it here. I already put the TFR. So if you had an ideal resistor, you can put TFR. Now, I think that's quite close enough for because I don't want to do the matching for you guys. I can only tell you that you can do the matching. This is close enough. Now this is only input match. If I go back to the intermediate match, you'll notice I had inductors, ideal capacitors. So your job is to replace this with the spirals, this with the P1500 capacitors, pretty much everywhere, wherever there's a. So you should have proper layout. Now when I said layout, what I meant there was, if I go to input match, right, so this is my input, like this is where the RF signal comes into the circuit. Look at my layout. This is the first point. It connects to the capacitor here. So I can get the capacitor. I can select these two. See, this snap together. It will snap. Then I can get that snap together. So it will snap. So this is pretty much making out your circuit. And then you'll notice I had another inductor here. I can either manually do this or ask it to snap together. Now you'll notice you didn't have that. So this inductor, I had to put this to get a better matching. So you'll probably do something else. I don't know, maybe you guys will put an inductor at this location. Now this inductor where we put the spiral, I can put it like that. And then you'll notice this is how the layouts coming together, but you'll notice there are things that run into each other. So you'll have to later, not in this review 2, change the shape of this inductor and all that, so that it will be a nice looking layout. So this is only input stage. So if I go back to my one level up and then look at the layout of the whole circuit, so this is what I've been making so far. And then I can get the transistor, put it there, but I don't want a transistor here. I want a transistor somewhere close by because I won't make the circuit. This is probably not the right transistor. This is the right transistor. I want to make the circuit as small as possible. So this is my first transistor, second transistor, input match. Then I'll have some circuit in between, intermediate match, some circuit here, output match, then I'll have the output. Now, so that's how the circuit will look like when you make the final circuit. You don't need that in the review 2. Layout wise, you don't need to do it. you only need to make it in the, so I'm stressing this point more, you only need to make sure you have MLIN components, inductors, capacitors from the PE1500 library at the end, at the review 2. You don't have to worry about your layout. It will come later in your review 3 and 4 because you will have to do EMing and then layout. I'll put more videos on EMing and layout in the next couple of days. So I think that's clear enough. Now that will take you to pretty much come up to noise figure. So we did this much, but I haven't really explained you guys before PSAT or OIP3 or P1dB. Now the reason I didn't explain them in detail is because we were planning to cover them in the lecture, so which will be in the next, after the break. Now, but you still have to plot them and check if it is fine. So I'll quickly show you how to plot them. Now if you want to make a PSAT, it's quite easy. PSAT is the saturated power at the output. So we look at the input power, we input some power into the circuit. Then we look at, so this circuit I'm talking about, input here, and look at the output power. And we increase the input power levels from like a lower power level to a higher power level and look at what happens to your output. It starts to go out from the linear region after a certain power level because transistors come in saturation. Now if you want to plot this, I have to make a schematic. So I'll create a schematic. I'll say PSAT or something. Create. So I need to have a sub-circuit. Of course that sub-circuit will be my LNA, and then that needs to have a power input port. So I'll have to get a port. Now if I remember correctly, the port was port with power sweep, port PS1. Now so that starts at a certain power level, say minus 10 dBm, not sure, so it goes to 20 dBm in 5 dB steps. Now remember, when you do this simulation, your whole AWR project is going to get slowed down because all these nonlinear measurements, nonlinear simulations take a while. So you can do this and disable later when you do the tuning. So now, so that's the PSAT circuit. I also need to set the schematic frequencies. It's a bit slow, but I want to set from 12 to 16 GHz, 1 GHz steps. Otherwise, this will take a long time for this particular PSAT measurement. Now I need to add a graph, new graph, say PSAT, a rectangular graph, that's right, and then I add a measurement. It's a nonlinear measurement, so it's a nonlinear power P-comp. Then my circuit is PSAT. I look at port 2. I would like to look at 12 GHz. Sweep frequency. So with the frequency used for x-axis, is that what we want on the plot all traces? So we will get the port for x-axis. Let's see whether this will work. dBm. Yep, that's right. So if you look at this, what it means, this is the input power in the x-axis. When you increase your input power, you will notice, I'll remove this. Notice when you increase your input power, so this is at 12 GHz, 13 GHz, 14 GHz, 16 GHz, 16 GHz, P5, 16, you will lose your linear rate. So if I plot this to a lower frequency range, say I will go back to my PSAT, goes to minus 30, and come back here, split this. You'll notice this is linear, right? So that means at your minus 30 dBm input power, you have about minus 5 dBm output power. So you have about 25 dB gain. That's right. That's it. That is your gain at whatever these frequencies. Now you'll notice slowly after a certain power level, you will go out of that linearity, and that is where you have your PSAT. So your PSAT spec is 13 dBm, which is around that range. So it's decently okay. 13 dBm. Yes, it's roughly right. So that should be good enough, I think. So that's how you check your PSAT. Then you also need to check your OIP3, that's intermodulation. We will also cover this in the coming up lectures. Now P1 dB and PSAT, you can read about it, but we'll cover it in the lectures. But this is how you plot it, and you can present this in your review too for your particular circuitry. And the other thing you can do is to add a new schematic for OIP3. Create. So when you do OIP3, you do the same thing. You make your circuit LNA, then you add a port. Now for this, the port is two-tone HB sources, and we do that. F delta is fine, and so we can put two lower signals. We cover this why we do it this way, and what's the significance of the OIP3, etc. in the lectures. So you do this. You do set up it like that, and you also need to remember to set the frequency range same as before. Easy. Yep. Okay, and then we plot a graph. It's a rectangular graph, so we'll say OIP3. Add measurement. So now in this case it's still a non-linear measurement, but intermode. Takes OIPN, and we look at our OIP3 at port 2. That's correct. 12 gigahertz, and that should be 2 minus 1, because so one signal is 12 gigahertz, other one's 11.9 gigahertz, and we look at the third node intermode products. Should do it. Okay, so OIP3 spec is 15 dBm. Now this is above 15 dBm, so this is already 69.8 or something. So we are fine, we meet that spec, so it should be okay. So we talked about now these three. VDD is 3 volt, that's your supply voltage. ID is the currents. Now how do you look at the currents? I think one of the students already asked me about this as well. So the currents, if you want to look at the currents, so you want to see the currents in these circuits. So let's see. So I put annotations. I'll delete this annotations. Right click, add annotations, go to current, apply, go to voltage, apply, and then when you simulate, it should pop up with currents and volts. So you will notice 12.6, 12.6, it's about 25.2, which is slightly above our spec. I think our spec was 1525. It's good enough, it's within the range, or almost in the range. So if you'll notice, if you pick a smaller transistor here, it will be within that. Currents will go down. .84 12.6, that's about 18 milliamps. But what happens is then you need to tune the input and intermediate match to meet the spec. I think that's in summary what you need to do, like help in getting a circuit right. So this is a 2-stage. You might select that you need a 3-stage. So you'll have input match, intermediate match, another intermediate match, third transistor, and output match. So that's up to you.